希望欢迎 Kevin。
Hi everyone. So can everyone hear me well? Good? In the back?
Yeah.
Okay, great. So hi, my name is Kevin, and I'll be talking about my project, Vehicle Action Prediction with Artificial Intelligence, an innovative way to transform advanced driver assistance systems from reactive to proactive. So first of all, let me give you an outline of what I'm going to be talking about today. We're going to start out with the motivation behind this project, the goal, materials, all of the development, essentially the procedure, and then we'll close out with a summary. So, why might this project be important? Well, first, 37,000 lives, on United States roadways, 37,000 lives are lost and 2 million are injured every year. And almost half of these incidents that result in these injuries and deaths, they involve two critical pre-crash events, turning and changing lanes. Now, in our vehicles, many of us have installed advanced driver assistance systems that can help with this. For example, forward collision warning, you have lane detection, lane departure warning, blind spot warning. And so these are able to give you a warning about 0.5 seconds before impact. Well, it's kind of observed. As a rule of thumb, we want 2 seconds to be able to have you react well in an emergency situation. So how are we going to improve this 0.5 second reaction time all the way to 2 seconds? Well, there's actually a lot of information that current advanced driver assistance systems, which I'll abbreviate ADAS from now on, ADAS, they don't use. What is this? Well, imagine if I were sitting in the next to the driver and you were the driver and you were driving. There's obviously a lot that you're doing that I can see. For example, you might be looking left and right, you might be slowing down, speeding up, maybe to overtake a car in another lane. So this information can all be harnessed for us to predict what you're going to do before you do it, so then ADAS can judge whether this is dangerous or not. And if it is dangerous, we'll issue you a warning. And what better way to do this with than artificial intelligence? So, what is the goal of the project? The specific goal. The specific goal is to improve this pre-crash warning time from 0.5 seconds all the way to 2 seconds, which is estimated to save over 8,000 lives a year. We're going to do this by harnessing all the information that ADAS has neglected to look at. We're going to look at your driver head rotation in terms of Euler angles. We're going to look at your vehicle speed, engine RPM. Are you accelerating or are you braking? Are you turning your steering wheel? And also where you are, your GPS information. And with all this information, our goal is to be able to predict these 5 things. Are you going to turn left, turn right, make a left lane change, make a right lane change, or just simply proceed forward? So these are the 5 classes that I'm trying to train the network to be able to predict and classify. So let's talk a little bit about materials. I split this into 3 sections. First of which are the sensors. We need to gather information to be able to train a network. So we're going to have the onboard diagnostics 2 interface. This essentially captures information about your vehicle, your speed, acceleration, your braking, your pressure on the gas. That's all in the OBD. And then we have a GPS. It's on a Samsung Galaxy tablet. Captures your location information, your bearing. We have a Galaxy S7 Edge that, with using the onboard gyroscope, we can measure your angular velocity in terms of your circular motion. So how fast you're turning your steering wheel, or if you're turning it at all. And then we have 2 iPhones serving as cameras. The iPhone 10 serving as the front-facing camera, and the iPhone 6 serving as the road-facing camera. Now, there's no specific reason that I used iPhone 10 and iPhone 6. They were just what were available to me. Now, next, we have programming languages to tie these all together. C++, Java, and MATLAB. And then software tools, open source, except for IBM, you have to pay a lot to use it. So IBM SPSS, it was used to perform feature selection. We can rank the collected features in terms of importance. We'll take the most important ones, we'll keep them, and then we'll filter the unimportant ones out. It's kind of like convolution, as Craig talked about in his lecture. And then the constrained local neural fields. This is a model that's convolutional neural network based. It is computer vision. And essentially, it maps your face, it tracks it, and then it can extract features about where you're looking. So those are the technologies and materials. So, how does this project work? I'm going to introduce to you the project development, or the procedure. We're going to start out with device sensors. Essentially, you mount these sensors in your car, and you're going to collect information from them. Data acquisition, which is when you actually click record, and then you start logging, so all of the information starts flowing in. But wait, you can't feed video into a traditional neural network. You have to find some features to give it in ASCII format, like numbers or text. So that's why we have data conversion. Using the CLNF model, we're going to take out your facial landmarks, 68 of them, your Euler angles in terms of your head pose, and then head orientation. And then from the road-facing camera, we're going to see if you have a lane available on your left and right that you can even turn to. And then after this, we're going to fuse that into one tabular data frame, which means everything comes together. We're going to model it, select features, throw it into a neural network, and then output the results. After which we'll take some analysis, and then we'll kind of adjust the neural network if we see fit. So that is the basic development of this project. I'll be going into greater detail with each of these sections right now. So these are the device sensors. It's pretty straightforward. We have the front-facing camera and the road-facing camera mounted in the dash area. We have the steering wheel data collection device mounted on the steering wheel. It's taped there. And then the onboard diagnostics 2 interface and the GPS interface is mounted right here near the seat. So all of these are going to be collecting information. Now what does that information look like? Well, from the 2 cameras we have video files, and then from the steering wheel, angular velocity, OBD2, and the GPS, they're all logging in CSV file format. And so just to give you an idea, the data that was collected totaled around 20 gigabytes. So that's what the data that we collect straight from the sensors looks like. Now, here is a specific part of that data collection, and that is the Android app that I wrote. I saw the need to do this because there wasn't one on the Android App Store, but essentially this one, it uses the gyroscope in your phone, everyone has one, and it measures the velocity at which you're turning it. And if you mount it to the steering wheel, you can get the angular velocity of your steering wheel, so I know how much you're turning. And then the OBD, the onboard diagnostics. This is something that you take, it's a piece of hardware, you take it, you plug it into the car, and then it will give you information like speed, engine RPM, torque, power, acceleration, gas pedal, stepping to a degree, and so on. So there are 196 distinct parameter IDs in total, which means 196 pieces of information collected. And so this tells me about what you're doing with your vehicle as a person. So we've got this data converted. We have the face tracking, we have the lane tracking, and then all of these into CSVs. So that is where, as we've mentioned before, you have to take the videos and you have to extract features from them. Now you might be wondering, what is CLNF? How does it work? So this is a software, open source software developed by a person at the University of Cambridge, and it tracks landmarks on your face, 68 of them, and then it uses these to calculate your angular, the motion of your head. That can be angular in terms of Euler angles and so on. And if you look at this video, it's tracking 68 points on the driver's head, and it's putting a box on there, so you can kind of tell, you can tell the yaw of the face, which way you're looking, left or right. And so that's the goal of this. All right, so now we've got 4 discrete sensor streams, 4 pieces of data, or 4 collections of data. We have to put them into one. So after we merge it, there are 563 features in each time step. So that's a whole lot of data. And if you, and we have them in one place. Now, you might be saying, okay, great, that's all the information we need. We throw it into the neural network, right? It'll run. That's what I tried, and that didn't work. You might be wondering why. Well, first of all, these 563 columns, not all of them are relevant. Some of them may be extra, they might be noise. And when you feed it into the neural network, if you have lots of data, you feed it in there, you might see overfitting or it just won't converge at all. And so that's why I asked a friend of my father's, she's a researcher at a national laboratory, and she recommended me to use some kind of feature selection tool. And that's why I used the classification and regression tree. So these are designed, of course, from the name you can tell they classify and they can regress. And based on this, they have the ability to rank the importance of features in a mathematical way. And so you can have the most important features at the top, least important ones at the bottom, and then you can find the line and then you can cut all of the useless features out. And when we run this, you can see that RPM is very important because when you're turning, you have to slow down, you can't just keep going. When you're making lane changes, you might speed up to overpass or slow down to get behind a car. And also, Euler angles in the z direction, your yaw. It's very important because your face, you tell us a lot by looking in different ways. And so the benefits of this, it's going to result in a better fit, mostly to combat overfitting, but also underfitting, and also improves computational efficiency because you don't have 500 features in each time step. And so yeah, it makes it run a little bit faster. So once you have all of that data, here comes the neural network part of this project. Recurrent neural networks were used, and these are essentially neural networks, but they differ from traditional neural networks in the sense that they not only take information from the current time step t, they also take input and output from the preceding time steps, times t minus 1 all the way to your start. And so what happens with this is you can learn from data with temporal dependencies. Something that happens here really depends on something that happened here. If you were going to turn, it really depends on did you turn your head in some kind of way a couple seconds before. And so that's why recurrent neural nets were used. Long short-term memory was implemented to combat a common problem of recurrent neural networks. And 3 phases were used: training, testing, and predicting. Now let's talk a little bit about what happened, what goes in and what comes out of the neural network. So, essentially, you have a bunch of sequences. What a sequence is all the data that describes what you did to prepare. So a sequence starts when you're starting to prepare for your turn all the way to the moment right before you turn. And so that's represented by a matrix. So each column represents the time, like time 1, time 2, time 3, all the way to around time 50. Because this is sampled at 10 hertz, that means about 5 seconds. So we have a bunch of data here. It's not easy to see, but I'll explain it to you. So the first row, it's categorical. It's a sequence number. It just helps me manage the data. It just helps me label, okay, this is a sequence 1, this is a sequence 2. And then the action class, the target. The target is the actual, what happened at the end of the sequence. I did some motions. I have to tell it, hey, at the end, he actually turned left. So that's what this does. And then the numeric data. This is the information that describes what you did during this time. You can see angular velocity, RPM, throttle, speed, Euler angles, left and right, lane availability. So that describes what happened, and then the output. That's what the neural network thinks you did before you did it. So that is what goes in and comes out of the neural network. And now, network layers and training options. So I'm not going to go into a whole lot of detail with the hyperparameters of this because these are really tuned on a trial and error basis. It really depends on what your data is, what your problem is, so that you can tune these. But essentially, you just try different things. Maybe it's RNG, but you can try different things, and then you can see what happens, and then optimize it for better results. So these are the parameters that were put into my network. And this is a piece of code that I used. It's a snippet of it. This describes the creation of the neural network, the definition of its properties, and also the training properties. For example, which optimizer are you using, your mini batch size, and so on. So this is just a snippet. And here are the development environments I used. I really want to point out one in specific because it's not, as far as I know, used a lot. Maybe people don't know a lot about it. But this is a really powerful tool, and it's really easy to use. You can see on the left, here's a flow. This flow is very simple, but it does really complex things. And the output is right here. It's the visual depiction of my classification and regression tree. And so what's really great about this is that you can analyze things with a lot of different outputs. And yeah, it's just a very powerful tool to take a look and get insights about your data. So now we have arrived to the results step. First question, how did it do during training? Was the data good? Was it bad? So this is the training accuracy and training loss over the number of epochs, which is just training it over and over again. You can see that the accuracy reached high levels and then the loss reached low levels, which means that the network can converge, the data is good, and your problem is legitimate. You know, there is a solution to it. So that is what happens in training. Now let's take a look at the confusion matrix. This maps the predicted class, like what my neural network said it was, and the actual class. And so if you intersect them, then this diagonal right here represents the number of activities, the percentage of activities that were classified correctly. And so you can see that the turns and lane changes were all hovering about 90%. And what was interesting is that straight was 71%. And I presume from my analysis of this that it might be because there's some noise. Maybe you're turning left and right, you're talking with your friends, you're taking a sip of water, whatever you're doing, there's a little bit more noise and it's not as distinguishable, but that's still a respectable number. So this is an interesting graph that I'd like to talk about a little bit more. The x-axis is the time to action, 4 seconds before you actually turn, and then 0 seconds basically when you turn. And if you'll take a look at this side, there's not enough information 4 seconds before you turn for me to make an appropriate judgment as to what you're going to do, because maybe you're just going forward. But then during this, at 2.5 seconds, you're starting to make preparations. Maybe you're slowing down, you're speeding up, and you're starting to look left and right. And so at that point, I can kind of judge, but I'm not confident. And then at 1.5 seconds, I'm pretty confident. You've done enough to show me what you're going to do in the next couple seconds, and I can make a confident prediction. And then at 0.5 seconds, when traditional ADAS systems are just being able to give you a warning, we're already at the verification stage, which means, oh, he actually did this, or no, he didn't. So this is the graph for turns. Now, we'll have the same graph for lane changes, and it's slightly different, because lane changes are inherently a faster motion. You don't do as much to prepare for lane changes because your car doesn't move as much during them. So as you can see, at 1 second, it's confident, at 0.5 seconds, it's verifying, and then at 2 seconds, it's beginning to judge. So, especially you can see from this turning graph, at 2 seconds, we're already able to give you an idea, that we are able to give ADAS an idea of what you're going to be doing before you do it. And so that's a really encouraging result. So, to summarize, what do we see from this data? First, the network can be trained to high accuracy and low loss. The network does converge, and the prediction can be judged at up to 2 seconds before collision. So, it's time to wrap up the project. What happened? First, 5 hardware elements collected data, 2 cameras, GPS, OBD, and gyroscope, and 20 gigabytes of data were generated, and it will be put on GitHub for public use. And this is quite important because there is no data set for this, just like MNIST, 60,000, there is nothing. So these were researcher generated, and I will be releasing it. And so, this project innovated beyond previous studies. The use of a recurrent neural network with long short-term memory versus a hidden Markov model. RNNs are the latest and greatest technology method to model temporal sequences, and just versus HMMs, they're superior. And then second, this is the first time CART has been applied to something of this nature for feature selection. And then third, the CLNF model from open source was used as opposed to the KLT face tracker that was baked into MATLAB. Now the difference is that CLNF is much more robust, it can operate in many more lighting conditions, and it gives you more information. KLT simply draws some dots on your face and you're left with that. But CLNF, they can extract these 3D features as to where you're looking, and so that's very important as well. So, what does all this culminate into? A system, a model, that can predict actions up to 2 seconds ahead, which is essentially 4 times what current ADAS is able to provide. And so this could save an additional 8,000 lives a year. So that about wraps up my presentation. Thank you for having me. It's been a lot of fun preparing and presenting to you guys. And I think it's especially an honor for a high school student like me to be presenting to a big group of big data professionals. So yeah. So thank you, and now I'll open up the floor to questions. Yes?
Yeah, so you said, so before you do it, you need to have to do the training set. So for each one, so for particular driver, you need to do the training, or so the model is only for one driver?
Right, and that's a great question, that's a great point. Because there's so many of us, 300 million in the US, many more in the world, we all have different driving behaviors, and I don't think it's feasible for me as a person to try to model everyone's behavior in the world. So yes, I train it on one person, and then I presume when this may be deployed, it's kind of like a warm-up time. When you first get your car, it doesn't know you, but we can automate the training of this, and then as time progresses, the network will be trained on your car, and then it will be able to learn to you. So to answer your question, yes, this is for one person.
Okay, thank you.
下一个问题。谁还有问题？
Very impressive presentation. I have a couple of questions.
Sure.
First, you mentioned 20 gig of data.
Yes.
What is your sample rate and how long is the data?
Okay. So I didn't. Okay. 20 gigabytes. The sampling rate was 30 hertz for cameras and 10 hertz for OBD and steering wheel. And so what I essentially did was 150 miles of driving in the DFW area. And so that's natural driving, so there might be a lot of, there is some highway data, there's some turning around in local, so it's a combination of those.
Okay, and I assume this is for offline processing, not live processing. Is that right?
Right, this is what I would call this is, yes, it's offline processing. And I don't really think there's a computational problem to make this a live stream. There are some like coordinating your sensors, that's just another programming challenge. But as far as, I think it's possible for it to be implemented live, but here it is offline.
So one last question.
Sure.
So any particular reason why you didn't use any of the common framework like TensorFlow instead of going with that?
Yes, that's a good question too. As Mr. V mentioned, this is my first go with machine learning, and I thought MATLAB is a great tool. It helps me get started. And honestly, yes, I've been thinking about moving to TensorFlow, and especially one reason is because the stochastic gradient descent, the optimizer, I really don't think it's the best one. I mean, it's been objectively proven that things like Atom are better and that those are supported by TensorFlow. So yes, I would like to move to TensorFlow in the future, but because this was my first go with machine learning, I used MATLAB because of its simplicity and its relative ability.
最后一个问题。
How do you prove that the data you collected from the outside scenario?
Right, yeah, that's a good question too. So I looked into lane processing techniques with computer vision that were automated. And what I found was, you know, they make it sound so good on GitHub, and then you look at the demos, and then you're like, okay, that's great, right? And then you run it on your own data, and it's like, oh, it doesn't work. So I did it by visual, manually. And I believe this is something that, you know, other researchers can improve on, but for now, the purpose of this project was not really to make a robust lane detection system, but I labeled it myself. And so when technologies are available, I'll move it around to being automated.
What did you label?
Oh, the road, right? I labeled if there's a lane available on the left and a lane available on the right. Because there's no way you're going to make a right lane change onto a curb, right? So that was kind of to simplify things for the neural network, because as you know, lane changes might be a little bit sudden and kind of, you know, a less information. So I just wanted to narrow it down for the neural network.
All right, thanks.
首先恭喜这个 Kevin， 哇，真的看到这 presentation 不仅是 impressive， 我觉得看到一个 the best candidate， 这个 young entrepreneur for the future。我觉得你应该去那个 Shark Tank。Shark Tank。我的问题是，就是你这个 prototype， 我现在看的，我觉得是一个 prototype。那我觉得从 commercial 的角度，或者说从这个 technology 的角度。有没有可能把这几个 component 给它 integrate， 变成一个 product， 然后当然可能讲得很远嘛，这个 product 目前你是用来做这个数据的收集和将来更多的 research， 那有没有什么 potential 这个 product 将来确实是能用到汽车上，然后来挽救更多生命？
Yeah, that's exactly what the hope was, because what I really saw was, you know, my mom told me a story when she was coming home from work, and she told me that one of her co-workers, they were driving on the road, they were doing something, and then when they were making lane changes, they were making a lane change, and then there was a car coming up behind her and she didn't see it. And then so she said that she was lane changing, and then there was like a warning. It was like, it was a beep or something. It was a beep. It was like, don't do that, and it beeped. And then she was like, just half a second later, I got hit. And so I really hope this is going to be applicable to commercial vehicles. Obviously, it has a ways to go, but yes, that is the intention.